example 1. And the newest thing that we're working on is we're trying to find local extrema. So I'm going to write that down here, local extrema. That means max, mins, and terrace points for an entire graph. So when I say local extrema, I'm talking about max, mins, and terrace points. 3 different things. Max, mins, and terrace points. And so the way we do this is we make what's called a first derivative sign chart, and that's what we're really working on. So here is my example. Let's say find all local extrema. Find all local extrema for f of x equals x plus the cosine of x. X plus the cosine of x. And since it's a trig problem and trig graphs go forever, I'm going to say on an interval on negative 2 pi to positive 2 pi. Normally there wouldn't be an interval for any other type of graph. Normally if there's an interval, then it's an absolute max and min that we're talking about, but trig functions kind of have an exception. So here's my setup. I'm going to go through the steps here. I need critical numbers in a sign chart. So I'm going to start by finding the derivative, f prime of x. Alright guys, so what's the derivative of x? 1 plus the derivative of cosine is negative sine of x. Let's set it equal to 0 and solve. So 0 equals 1 minus the sine of x. And let's add sine of x to the other side. So when does sine of x equal 1? So it just requires you to know your unit circle. Think about the unit circle for a second here. I'll draw a little mini circle. When is sine equal to 1? And I'm thinking about sine is the y value. So right here at 0, 1. At the top of the unit circle seems like the best answer. So that would be pi over 2. The trick on this one is look at the interval. The interval's from negative 2 pi to positive 2 pi. So if this is 2 pi right here, this is 0, but it's also 2 pi. When you go one lap around the unit circle, that's from 0 to 2 pi. But you want to go back to negative 2 pi, so you also have to think about going one lap backwards. So where else could this happen? If you're going backwards, it could also happen at 3 pi over 2. But it would have to be negative. So we're going to have 2 critical numbers. I don't know if that made sense, so I'm going to try and rewrite this here for a second. The 2 critical numbers are going to be at pi over 2 and negative 3 pi over 2. Think about what negative 3 pi over 2 means. It means if you start at 0, go back 3 pi over 2, that's a distance all the way back to here. So pi over 2 at the top of the unit circle is also the same location as negative 3 pi over 2. If you were going backwards, I hope that makes sense. So 2 critical numbers fall in this interval, and we're going to set up a sign chart to kind of match this. So next step, draw a chart. And we're going to label it the sine of f prime of x on the top, and then the behavior of f of x on the bottom. So sine of f prime of x and behavior of f of x. We're going to put our 2 critical numbers on there in order, so the negative one's going to go first. Negative 3 pi over 2 is going to go right here, and positive pi over 2 is going to go right here. And now our job is to select some numbers in between these intervals that we can really plug back into f prime to figure out the sign. So the easy one in the middle here will be 0. That's going to be simple to do. After pi over 2, why don't we do like pi? I'm trying to pick easy numbers. And before negative 3 pi over 2, I'm going to have to go back on the unit circle. I can't go all the way back to 2 pi because that's the end of the interval. So I'm going to do negative 11 pi over 6. Something that I can at least work off of. And then we're going to plug all these in. So we need to find, let's put a little note down here, f prime of negative 11 pi over 6, f prime of 0, and f prime of pi over 2. And with these three values, we'll be able to finish our chart up. So negative 11 pi over 6, remember what our derivative was? It was 1 minus sine of x. So it's going to be 1 minus the sine of negative 11 pi over 6. 1 minus the sine of 0. And 1 minus the sine at pi over 2. Oh, not pi over 2. Pi. There we go. 1 minus the sine of pi. I knew something was off. You guys got to tell me these things, even though I'm on a DVD right now. Okay, so 1 minus the sine of pi. Okay, so anyways, back to plugging these in. Sorry for the run-on sentence, but I want to fit it on the screen here. So sine of negative 11 pi over 6 is going to be a half. So we're going to have 1 minus a half. Sine of 0 is 0, so 1 minus 0. And 1 minus sine at pi is negative 1. So we get a half, 1, and 2. Check out what we get. Remember, the numbers don't really actually matter. It's just that this is a positive number, and a positive number. That's really all that matters. So on my sine chart, I'll do this in a different color. We've got positive numbers, and more positive numbers. That's all we got is positive numbers. So the graph of f of x must be increasing, increasing some more, and then increasing some more. So it goes up, has a critical number, goes up, has a critical number, goes up. So that makes both of these points, these critical numbers, flat spots. Terrace points is what we call them. So terrace point here and a terrace point here. I kind of want to verify this on a graph and use our calculator because I want to show you something about these. These graphs are really unique. So let's do this. Let's get this on the calculator now, and we'll add it to our notes here. So go to your y equals, and let's type in this function. We're not graphing the derivative, we're graphing the original graph. So x plus the cosine of x. So get x plus the cosine of x into your y equals. And then I'm going to hit the zoom button here. And I want to zoom this to a trig window. So I'm going to zoom. I'm going to do number 7, z trig. Get a nice trig window. And look at this graph. Okay, I don't know. Does your graph look like mine? I can't even see what's going on here. So I'm going to go to my window. I'm going to play with it a little bit. Oh, my zoom didn't work. That's weird. Let's try this again. I think I had the wrong mode on. Still looks weird. Okay, so if I play with this, there we go. I was in degrees. I had to switch to radians. Okay, so here's my graph. It's looking good. This is from negative 2 pi to 2 pi. You can kind of see what it's doing. It goes up, flattens out, goes back up. I can't really see the bottom of my graph here, so I'm going to tweak my window just a little bit more. The y-axis goes, for me, negative 4 to positive 4. I want to go farther down. I'm going to go to like negative 8. I don't know, something like that. There we go. Just so I can see a little farther down on the graph. Look, there it is, increasing, flat spot, increasing, another flat spot, increasing some more. So, okay, that matches my sine chart. 2 flat spots, 2 terrace points. Let's draw a picture in our notes of what this graph looks like. So let's see here. We've got a graph that goes something like this. It goes from 2 pi and negative 2 pi. And the flat spots are happening at pi over 2, right about here. And negative 3 pi over 2, back here. And so it looks like the graph kind of goes like this. Call this f of x. So we can kind of see that right around here is a terrace point, and right around here, so I'll write TP for terrace point and TP. The reason I wanted to draw this out is just to kind of have it in our notes with our sign chart. It kind of verifies that the whole entire graph is increasing, and there's actually a name for this. When a graph increases like this, it's called strictly monotonic. Strictly monotonic. And basically what that means is the graph is always increasing. If it's strictly monotonic, it never changes from increasing, decreasing. There's no max and mins. So I'm going to say for my definition down here, a function that is always entirely increasing or always decreasing. So you can have a strictly monotonic graph that's always going down, always decreasing. Like it could go down, flatten out, go down, flatten out, and that would be monotonic as well. It's just as long as it always goes one direction. So a function that is always increasing or always decreasing, I'm going to write dot, 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 with the exception of flat spots. With the exception of flat spots. Of flat, I guess I should say flat points, terrace points. So it's called a strictly monotonic function. So sometimes you're going to see this when you're building your sign charts. There's not a lot of these out there, but there's enough that you'll run into them, and you'll see them in the homework for sure. So it's called strictly monotonic, and don't be afraid. Like if you get that as an answer, nothing's wrong. It's just sometimes the graphs look like this.